So you can just click on this link at the top, and that'll take you to the list. So I would just recommend just downloading all the example code, just so you've got it on your hard drive. And when I start using it, you can open it on your computer and maybe even follow along. Okay. Okay, so today's presentation is going to be on creating, building, and using scientific software, and this covers pretty much any kind of software. So this might be matrix libraries, it might be build systems, any number of things. Okay, so my outline for today is going to cover 3 basic points. I'm going to start with the basics, define some terms. Give some sort of basic concepts. Then I'll go into creating and building software. So this is the build process. The build process can be thought of as three-step or three-tier approach, 3 different approaches. There's small projects. These are order 1 people and order 1 files. This is something, maybe you're developing a small standalone CFD code or something like that. Then there's medium-sized projects. These are order 10 files or order 10 people. So, getting larger, you have to do a little more project management with the code. And then the last is large projects. And pretty much any open source project falls in this category. This is order 100 or more files or people. Okay. Then the next thing I'll talk about is using software, specifically using third-party packages. And I'll talk more about this process that I've drawn here, but essentially this is the process of taking stuff that third-party software provides to you and using it in your program, in your code. So for example, you could download a linear algebra package, and you would be able to use the different classes and methods and solvers that are provided through that package. Okay. So I'll start with software, the basics. When you want to create a program, you have to write it, and when you write it, you're writing it in a source code or a computer language. This is a high-level language, something that we can understand, something that when we read, we understand what it's doing. Things like C++, C, Fortran, these sort of things. But my processor, which is ultimately doing all the work, my processor doesn't understand C++. It doesn't know what a bracket is, it doesn't know what vector is, it doesn't understand these sort of things. So the processor speaks assembly language. So there's the people language and machine language. And so there has to be some way of translating something that we understand into something a processor understands. Because all the processor understands is, pop, push, move, call, these sort of very low-level commands. So this is what compilers do. They take our source code language and they convert it into assembly language so the processor can understand it. I've listed a couple of common compilers here. The GCC is probably the most common, and it's on any Linux system. There's also the ICC, and there's a whole range of compiler suites. I listed a few in the last workshop. So for the GCC specifically, on the command line, GCC refers to the C compiler. G++ refers to the C++ compiler, and Gfortran refers to the Fortran compiler. So let me give you an example. Okay, so I'm going to run 2 very simple Hello World programs. Okay, So I'm going to, so I have hello world.c. Can everyone read this okay? Does the font need to be bigger? Okay, let me minimize this. Okay. So if I want to compile this simple C program, I say GCC, and I'm going to add a flag here, -G. I'll talk about that in just a minute. Hello world.c. And then I tell it where I want it to put the output. So this is the name of my executable. So I'll call it hello from C.x. Okay, so my compiler creates an executable. We can see it here, hello from C.x. So I can run this just like I run any program. And we can see that it's printing hello world, this is C. So when I run it, it prints hello world, this is C. Okay, so this is pretty basic. Just basic C. So I can do the same thing with a C++ program. So this time I'll use G++, and I'll point it to hello world.cpp. The extension is different because it's in a different language. And I'll tell it the same thing, -O, and I'll tell it where I want it to put my executable. And I'll call this hello from C++.x. So it's compiled it, and if I list the files, I can see it's right here, hello from C++.x. And if I run it, I say hello from C++.x, and it prints this statement. Okay? So this is, hello world is sort of the first program you learn how to write when you're learning a program language. So we've just, run through a hello world program for C and C++. Now, where's my presentation? Okay, so the key between translating from our language to a processor language is architecture. This is the type of processor you have, and it's sort of how your processor interprets commands. So if you want to know what type of processor you have, you can run the uname command. So I'll do the same thing I did last time. I'll just write sort of collection of commands that we're learning. So you can run uname from a command prompt. So let me give you an example of this. So if I run, So if I run uname-p, I see that my processor type is i386. Okay. Now if I log into Updraft and I run the same command, uname-p, I'll see that it's a different type of architecture. It's a 64-bit processor. Okay. So something interesting we can do is take this executable that we created and look at what the actual assembly code is that the processor is running. So you remember I compiled with this -G command, and I mentioned that I'd talk more about it. So the -G command tells the compiler to output extra information. And that extra information can be used by a debugger. So a debugger is a program that you can run other programs through, and it'll interpret what's going on in that program. So if a program crashes, the debugger can tell you what was going on in the program, what the state of the program was when it crashed. So the GNU debugger is pretty ubiquitous. So I started up using GDB. Well, actually, I started up using GDB, and then I tell it what executable I want to use, or I want to run through the debugger. So I'll run this simple C program through the debugger. So it loads the program, and if I type run, then it'll run the program. And I can see, okay, it prints hello world, this is C, and it exits normally. So what I want to do is I want to see what happens on the processor level when I run this main function. When it actually wants to printf hello world, this is C. What's happening on the processor level? So I can give a special debugger command. It's disassemble, and then I give it the name of the function, main. So this is what the processor is doing. It's pushing, it's moving, it's it's calling subroutines, it's leaving, it's moving, it's calling. It's doing all this, processor stuff. Okay? So now I'll do the same thing on a different architecture, on a different computer. So this is the same program, compiled the same way, with the same compiler. And if we type run, it'll do the exact same thing. But when we type disassemble main, we see something totally different. There's fewer calls. These addresses are a lot longer because it's 64-bit. Here they're shorter because my computer is 32-bit. So when we look at the assembly code on Updraft, on a supercomputer, it's completely different than the assembly code on a Mac that's running on an Intel processor. Okay. Okay, so I'll just write these commands up there really quick. So we just learned the GDB command. We also learned some commands in GDB, specifically run and disassemble. Okay. And so disassemble just gave us the assembly code for whatever our function is. So I also want to give a few more terms. When people talk about binaries, when they're talking about programs, they're referring to the actual compiled assembly code. So if you go to an open source project's webpage, you're given the option to either download the source code or download binaries. And when you download a binary, you have to pick what your operating system is and what your architecture is. And a perfect example of this is if you're running on a Mac, you have to specify whether you're running on Snow Leopard or Leopard. And the reason is Leopard is 32-bit and Snow Leopard is 64-bit. And so as we saw from this simple example, the actual assembly codes are completely different for 32 versus 64-bit. There's also this distinction between debug and optimized binaries. So I mentioned debug binaries. When you build a debug binary or when you compile a debug executable, it puts extra information into that executable so that a debugger can understand what's going on. There's also, and so that's going to slow it down because there's all this extra information. But there's also, on the flip side, you can speed it up. using these optimized, different levels of optimization. And so what this is going to do is it's going to look at your code, and let's say you've got 6 nested for loops. So what these optimization techniques are going to do is it's going to figure out how to disassemble those for loops so that the machine code can run faster. The trade-off is a debugger is not going to have any clue what's going on because everything's been rearranged and disassembled so that it runs faster. And so these are all flags that you give to your compiler. So for example, if we're using GCC or G++, the -G flag gives us a debug binary, and the -01, -02, or -03 gives us an optimized binary. And the levels of optimization are just the aggressiveness of the techniques that are used. Okay, so this is fine for hello world programs. These are just single files. But what happens when we have an object-oriented code? Now we've got several files scattered throughout, and this file is using that file. We have these dependencies among files. So an object source code will define objects, and then other objects or drivers will use those objects to do things. And the idea is to abstract what the object how the object does what it does in the object file, so that the driver can just use the object however the methods happen to be defined. So this is just a simple example, and these are on the website as well. So I've just defined a simple class A. So A has, you don't need to worry about the C++ syntax for now. The main thing to note is that it's got this echo function. And this echo function is just going to print this single variable, x. So we create an object A, and we pass a number, and then when we call echo, A is going to print that number. And then we have a driver, which creates an object of type A, and passes a number. The number in this case is 5. It tells A to print that number, so it's going to say x equals 5, and then it's going to delete that object. Okay, so the header file contains declarations of a declaration of this A class, so that other classes like this driver class can use it. And the way that's done is using these include statements. So what that does is it tells the compiler to take a.h. So it takes this whole file and just sticks it right there verbatim. It's just a copy and paste into that file. That's basically what happens. Okay? And same here. We're just copying a.h and pasting it into this file. And that's exactly what the compiler is doing. Okay? So the way we compile this is using 2 steps. First, we have to compile our object. So we use this -c argument, and what that says is compile this object, but don't finish compiling yet, because we're not done yet. So the compiler won't complain that there's no main function and it doesn't know how to run this. It's just going to make a file called a.o. And a.o is just the source code, the assembly code for the class A. And then we compile the driver, and same arguments, -o to tell it where to output our actual executable. And this time we're telling it a.o on the command line so that it knows when we say create an object of type A, it knows what A is, because A is defined in a.o. Okay? Okay. So let's run this. So I've got a file a.cc, a.h, and driver.cc. So these are the three files that I showed you in the presentation. So we're going to run g++ -c, a.cc, and this should create a.o. But it doesn't. Okay, it throws some errors. It says, I don't know what a.h is. I don't know what class A means. I don't know, what echo means. I don't understand any of these things you're asking me to do. Okay? So the problem is the compiler doesn't know where a.h is. The compiler has a certain list of directories where it's looking for a.h, and it can't find it in that list of directories. So what we have to do is tell the compiler where to look. So we do that by including a -i, which stands for include. So this just tells the compiler, here's some extra places to look for header files that I'm going to use. And I'm going to put a dot, which means the current directory, and it compiles fine. It says, okay, that's fine. I can find a.h. I know what a is. I know how to find the things you're asking me to do. Okay, and we can do the same thing with the driver. We compile the driver, but we see some more errors. Driver doesn't know where to find a.h. Doesn't know what kind of object I'm creating. It doesn't know how to call echo because it doesn't know anything about that. So we have to tell it where to find a.h because we included a.h in our file. So we do the same thing, -i and the current directory, and it'll compile fine. And then we can run our executable, and it'll print the number. It'll print x equals 5. Okay? Any questions about what I'm doing or this process? Yes?
I've been able to compile code that has include statements, that includes files, and as long as they've been in the current directory and haven't needed a -i. Do you know why that is?
I don't know.
So are you using quotes for your includes or angle brackets?
Quotes.
That's the reason. Quotes on includes will include the directory that the file sits in. Angle brackets says you've got to have a -i with a path.
So why use angle brackets?
Because it's a little safer than quotes. If the header file is always in the same directory as the source file, then use quotes. If you're pulling it from somewhere else, it's generally safer to use angle brackets, especially if you don't have direct control over the full source tree, because if somebody changes that and the builds it, anyway, it's generally safer to use angle brackets, unless it's always sitting in that directory.
Okay. So we saw that we needed to add these -i and the current directory in order to tell the compiler where to look for these hash include files. Okay. So this kind of covers small projects. If you're building a small project with a couple of files, you can do everything from the command line. You can call G++ or GCC directly. Okay. So a one-shot command is perfect for those situations. But with medium projects, you start to get more files. Interdependencies get a little more complicated. Maybe this object requires that, depends on that object, which depends on that object, which is used in the driver. So maybe things aren't as cut and dried as they were with 3 or 4 files. You might also have multiple directories. So things might start being organized into directories, and so now you've got to manage the directories. So the G++ commands, running those directly takes more time and it gets more complex. So I'm going to talk about ways to automate this process. So rather than running these individual commands for every piece of source code, we can use some tools to automate these things. Another reason we might want to look into this is if we have 20 or 30 files and we only touch one, maybe one line in one file somewhere, we don't want to have to recompile all 20 files or all 50 files. That would waste a lot of time. And really, there's only a few files that are actually going to depend on that. So we need a smarter way of generating these compiler commands. So this is the use of a tool called Makefile, or called Make. So the way Make works is you give it a Makefile where you define certain targets. You say what those targets depend on and what commands to run to create those targets. And when you type make and you feed it this Makefile, Make is going to run the commands that need to be run. So if something's already up to date, it's not going to rerun it. It's just going to say, okay, that's up to date, I don't need to recompile it. So there's sort of three ingredients to a Makefile. The target, so we define this is our whatever's in our -o, whatever we want to build. Okay, so in the case of our object A, we wanted to make a.o. In the case of our driver, we wanted to make driver.x, the executable. Okay. The second ingredient is the files that depends on. So to build our object A, we depended on the A source code and the A header file. And in the case of the driver, we depended on the A header file, and we also depended on the driver, the actual driver source code. And finally, we give it commands to run. So these are the G++ commands that we want it to run. So in this case, we're running G++ -c, a.cc, just like we saw in the command line before. And then in this case, we're running G++ and we're giving it -o driver.x to build the executable. Okay. So the way we make these is we type make a.o and make driver.x. So this is pretty straightforward. If we want to make driver.x, we type make driver.x. Okay. Another nice thing about Makefiles is we can define fake targets. So instead of saying a.o or driver.x or something we actually build, we can just put words here. So we could put all. This would be, make all. So this would make everything. And we could put two other targets that would have to build. So now when we run make all, it says, okay, I need a.o. And it's going to look in all the different targets. It's going to say, is there a target named a.o? And if there is, it's going to try and make a.o. Then it's going to say, okay, I've got a.o. Now I need driver.x. So it's going to look and see if there's any targets named driver.x. If there is, it's going to try and make driver.x. And then once it's done, I haven't given it any commands. So it's going to say, okay, I'm done. I made everything I need. I found everything I needed to, and I don't have any commands to run, so I'm done. You can also give it system commands. So this make clean is an example of a system command. This is a pretty common target if you want to remove the sort of intermediate object files and driver files. So you can give it a system command, like remove a.o and remove driver.x. So if you wanted to start over, if you've changed the code a lot and you wanted to start over, you can type make clean to get rid of those files and then recompile from the beginning. And as I mentioned, if the compiled code is already up to date, if driver.x is already up to date and you haven't touched driver.cc, then it's not going to remake it. Okay, so let's just look at an actual Makefile to see what this looks like. So I've got my make file here. It's the same one I just showed you on screen. I've got a couple targets default. So this is going to be the default target. If I just type make and I don't say what it should make, this is what it's going to do. It's going to look for one called default. So I make a.o and driver.x. Then I also define a make clean. And then the a.o and driver.x are just like they looked in the presentation. So when I type make, so I type make clean, and it'll remove the object file and the driver file. And then I type make, and I can see it runs two commands. It runs these two commands, the two commands I specified in my make file. So when I type make with no target, it's going to make the default. And when I want to make the default, it's going to make a.o and driver.x. And a.o runs this command, which we can see right there. And driver.x runs this command, which we can also see right there. So are there any questions about this? Any thoughts, any comments? Okay. All right, then I'll move on.
I'll ask a question.
Okay.
So if I make a change in a file that is included in 50 other files,
Uh-huh.
then if I run this make command, it makes the adjustment in all 50 of those files.
Yes. So in the make file, what I'm saying is, let me delete this comment.
Only if you explicitly put in the dependencies on that header file in all of the 50 other files. If you don't
Yeah,
put
so-
it in, it doesn't know it depends on it.
So when I want to make something, I have to specify what I need to make that.
I see.
So if you are including 3 or 4 header files, you'll have to put these header files in the list of files that you require in order to build that file. If you don't, and that header file happens to be there, everything will go fine. But if it's not there, then you're going to get a compiler error. But if you include it in the list of files you require and it's not there, then you're going to get a make error. Make's going to say, I can't make this because this file is not there. Okay. So if you include all the files that you need, let's say you include 3 header files, and you list all 3 of those files on this line where you list the files you need. So I would include my 3 header files there. Then when you touch any of those 3 header files, make is going to look at the list of files that target depends on, and it's going to say, oh, one of them was touched. I've got to remake this. So let's say I touch driver.cc. A.o doesn't care about driver.cc. It just says, I don't care. I don't need to remake myself because what happens in driver.cc doesn't concern me. But the driver.x target depends on driver.cc. So that's going to be remade.
Gotcha.
So if I type, so I've already made everything here. And if I type touch driver.cc and I run make again, so I've touched driver.cc, so I've done something to it, and then I run make. Make's going to say, okay, I don't need to rerun gcc or g++-c a.cc because a is fine. But somebody touched driver.cc, so I have to remake driver.x. Does that make sense? Okay. So another nice feature of makefiles are these things called macros. Rather than hard coding everything, which would kind of have the same problems that we had before running single command lines, instead now we can use makefiles to define macros. So macros are basically variables. We define a macro saying macro name equals some string. Now these macros can hold names of compilers, flags for compilers, names of files, lists of files, directories, any number of different things. There's also these special macros. So there's a macro for if you have a list of source code files. So let's say you have a list of .cc files, and you want to replace all those suffixes with .o. You can just use a really simple one-shot line in make, and it understands that this means every time you find .cc, replace it with .o. So you don't have to redefine the same list twice if you want one list with .cc and one list with .o. You just use this single command. There's also a macro for saying insert the name of the target here. So in the case of the driver.x target, if I wanted to say -o driver.x, well, if I go back and change the name of the target, I have to change the command line too. But instead, I could just put $@ and it would automatically change that for me. There's also a macro for inserting all the required files. So if you want to, if it requires a bunch of .o files, instead of reproducing that long list on your command line, you just put $caret and it automatically sticks that list on your command line. And there's a macro for inserting the name of the first required file. So if you have one required file that in particular that's special, maybe it's the .cc file or the source code file, and you want to treat that one differently than the rest of the list, you just put $. So there's some really convenient macros provided in Makefiles. And these can make Makefiles much more general and much more powerful. So if you're not using macros, then you're not using Make to its full potential. Okay, so Makefiles, we saw they automated the process of building. They can speed up compile time by only compiling on an as-needed basis. You can do a lot with a little. Using these macros, you could compile 50 files using 3 or 4 lines of Makefile code. But there is a problem, and the problem comes when your projects start growing larger. So Makefiles can become difficult to manage. One user might want to specify this is the directory where some third-party package is. Maybe another user wants to specify a different directory. Maybe one user wants to use this compiler. Another user wants to use that compiler. So as you get more and more users, and as you get more and more source code, these Makefiles get more complicated, and the users have to sort of learn the Makefile code, how to write Makefiles in order to just build a program. So we saw that Makefiles work great for these medium projects where you've got maybe 10 people, maybe 10 files on that order. But as these start growing in size, large projects, you might have 10 or more directories, you might have multiple programming languages, you might have hundreds of users, so things get a lot more complicated. So is there some way that we can take all the stuff on our computer, wherever it happens to be located, whatever programs we need, whatever libraries we need, whatever architecture our processor is, whatever compiler we want to use, and have something that'll just figure that stuff out for us and then make a Makefile, so that we don't have to dig into Makefiles just to build a program? Well, you're in luck, because there is. Okay, so these are build systems. Build systems, they do exactly this. They take all the stuff on your computer and they figure out where it is and what it needs, and then it feeds that into a Makefile. So that all you have to do is type make. And the Makefile will figure out where things it needs are, and you can put your libraries in weird places and the Makefile doesn't have a fit. Okay? So we're going to talk about 2 build systems today. I'm going to talk a little bit about GNU Auto Tools, which are sort of the most ubiquitous build system, and Professor Sutherland's going to talk about CMake. So I got this diagram from Wikipedia. This shows a flowchart of how AutoTools works. So I'll talk about some advantages of AutoTools. This is what the user does. So it's really easy. This is the advantage of AutoTools. The user literally types 3 commands. /configure, this means run configure that's in the current directory. Make and make install. Sometimes they don't even have to run make install. Okay, so for the user, this is like compiling software for dummies. It doesn't get much easier than this. You may have to give some arguments to configure, but for the most part, this is really simple. This is the disadvantage. This is all the stuff the developer has to do. So usually you don't learn AutoTools. You just have somebody you know who knows it, and you ask them to write your configure file for you, and then you give them, you know, cookies and Jolt soda and teddy bears, and then you never think about your configure file again. And actually, AutoTools is sometimes called AutoHell by developers. So not only is this a complicated, tangled process, but it's not easy to learn. Okay, so let me just go over the user end of AutoTools. I'm not going to go at all into how you write configure files. I'm going to go into how you run them. So configure is what finds all that stuff on your computer. You run it just like any normal script, and it goes out and it says, okay, where's this program? Where's that program? Where's this library? Where's that library? And it's going to figure out where things are. Sometimes it'll get confused because just like a compiler, it has a list of places it's going to look for things. And if it can't find something on that list of places it's looking, it's going to get confused if it can't find it. So you can give configure scripts options, and they'll almost always take several options. And these options can point configure to different libraries you have if they're in unusual locations. It can turn features of the program on or off. So if you wanted to download let's say you wanted to download a linear algebra package and you only wanted dense solvers instead of sparse solvers, or whatever, you can turn these on and off using configure. And it'll automatically create the make file that'll turn those things on or off. You can also tell it where you want to actually install this program. So if you don't want to install it in the world accessible place, if you want to put it in its own directory where you have control over it, you can do that too. And this .configure --help will give you all the information you need to figure out what kind of options this configure script can take. And then, so you run configure, you see a bunch of stuff flash across the screen. It says, okay, I'm looking for this, I'm looking for that. And then it's going to create a make file when it's done. So then you run make and make install, and that'll install the program. So there's a few common targets I'll just mention here. Make is making everything. So this compiles the source code, it creates libraries, it arranges everything it needs to, and it does all of that in place. So everything is compiled into the same directory where you actually run make and where you actually run configure. So if you download a folder and you call it source code and you type .configure and make, then it's going to compile all that source code, but it's all going to stay in source code. And then when you type make install, it copies everything that it needs to copy to whatever directory you specified as the install directory. So it's not actually installed until you run make install. And then the last one I mentioned, make clean. So make clean, in most of these cases, make clean is just going to get rid of everything that make will create. So all these things that you're compiling, all these objects and libraries, make clean will just blow all that away. Okay, and so we're what I'm going to do is run through the rest of the presentation, and at the end, just take a short break, and then after the break, we'll actually run this process for a couple of programs, so you can kind of get your hands dirty and see what it, see what all this stuff really means in practice. Okay. At this point, I'd like to turn it over to Professor Sutherland for his CMake presentation, and he's got a web address for the PDF of this presentation.
Oh yeah, that'll probably help. Although, so I thought you were going to have them build CMake. Does anyone have CMake installed on their computer? A few of you do.
Are you recording?
Okay, we'll do this slightly different.
So if you want, I can, skip to CMake right now.
Do you want to have them just build CMake?
Okay.
I've got to. Yeah, let's do that, and that way they can actually use it.
Okay.
Okay, let's do
Sounds
that.
good.